In this section, 9.5, we discuss the concept of angular momentum, which is the counterpart to linear momentum. Now you recall that linear momentum has the form of mass times velocity. Well, you could probably guess by now, by looking at the comparison of the equations that we've had, that this is translational, that the angular momentum L, I should have written that as P, excuse me, that the angular momentum L is going to be equal to the moment of inertia times the angular velocity. The concept of mass times the concept of velocity. And that's exactly what happens. Just in contrast to the momentum P up here, we have the concept of the angular momentum L, which is I times omega. But we can't just invent things. They won't be useful. So we have to figure out how this is justified. So we're going to begin by saying, what is our torque? Our torque is R times our force normal, or force perpendicular. And our force perpendicular is change in P over change in T. So this is R delta P over change in T. Well, this is R times the mass times the change in V over the change in T, assuming that the mass is constant. So now we have a change in V, and we know what the change in V is. It's R times the change in omega. So this is equal now to Rm, and now this delta V, remember V is equal to R omega, so this is going to be R times change in omega over change in time. And now we've got the change in omega over change in time. And if we look back here, this is m times r squared, and this is alpha. And so this is going to be, on the one hand, I times alpha. But we can also take this as, take the change and bring it back all the way over to here, because these are constants, and write this as the change in I omega, where this is I omega dt, and I omega is now equal to L, change in L over change in time. So whether we look at how the torque is built as I alpha, so we can say this first equation we derived says torque is equal to I alpha, that's like F is equal to ma. And here the second one, we see that torque is equal to change in L over change in time, or better yet, dL dt. That's comparable to the equation that we've previously had, where F is equal to dp dt. Again, the change in something over the change in time is equal to this force. Here the change in something over the change in time is equal to the comparable force. That means this is angular momentum like this is angular force. So we have now proved that our angular momentum is effectively I times omega. And so I'm going to write that a little bit clearer over here. L is equal to I omega. And we have torque is equal to change in L over the change in time, or I times alpha. These are critical equations. And here they're derived. We could equally derive them with calculus using a derivative rather than a delta, and then it works out just perfectly. If we have an ensemble of particles, then it really doesn't matter, because you recall their alpha is all going to be the same. When this solid object is rotating, then every object is rotating, has the same angular acceleration alpha, so that always factors out, leaving the term I times alpha, and that compares to F is equal to m times A. Now we can look at different problems associated with this and say, well, if the angular momentum is going to be constant, then there is no change. And we can look at the angular momentum from one time to another time and say it must be the same if there's no torque. One perfect example of this is a skater who spins around on one skate, one ice skate, and they spin around this point and they take their arms and they hold them out here and they take one leg and hurl it out in this direction. And as they begin to rotate, they then bring their arms in, bring their leg in, till they make themselves such that their mass becomes very close to the center. When they do that, of course, they change their moment of inertia. They change I. And since we have I times alpha as L, then if I gets smaller, alpha must increase. Well, let's show how that actually works. And we're going to do that by taking a person and letting them just hold two objects out here and stand on a rotating platform. This is an experiment we often perform, or demonstration we often perform in class, where this platform can rotate very frictionlessly. And people take a weight and they hold it out, and then we spin them around with some angular velocity here. So let's imagine that we do that, and then they bring this mass in, and we're going to ignore the mass of the person. So we're going to take, let's say, a mass of about, 1 pound, we'd have 2.2 pounds would be 1 kilogram. We'll take about 4.4 pounds in each hand. It's 2 kilograms. We got 2 kilograms in each hand. And remember, this is about 1 meter. So you can stretch your arm out to about 1 meter. So, and we're going to turn you around so that you rotate, let's say, once every 2 seconds. So your angular velocity is going to be 1 revolution in 2 seconds. Okay, let's break this down now, because it gives us a good example of how to compute these angular quantities. What is a revolution? A revolution is 2 pi radians. We're going to divide that by 2 seconds. So it means that our angular velocity is equal to pi. Omega is equal to pi for a person who is rotating around so that their right arm goes around 1, 2. It's pretty rapid. Now we already know what the moment of inertia of this person is. They're really just a stick figure. And so we can look at what the distance is out. It's 1 meter. So what is our mr squared? Remember, I is equal to mr squared. And so we actually have 2 of these. So we're going to have mr squared twice, which would be 2 times the mass. The mass is 2 kilograms, times the distance out squared. Well, that's 1 squared. So I is going to be equal to 4. And remember again, that's kilogram meters squared. So I is going to be equal to 4. So now we know what I is and we know what omega is for this person standing on this rotating platform. And so we can say L initially is equal to I omega, which is equal to 4 times pi. Well, that's what it must equal to finally, too. However, we're going to change I and change omega. And what is our new I going to be? Well, we're going to bring these masses in to, let's say they're only 1/10 of a meter. Rather than a whole meter, let's say they're 1/10 of a meter. And see if we can compute what omega would be. So this must be equal to, what is our mass going to be now? Our new moment of inertia, this is the initial one, initial and initial. The final moment of inertia is going to be equal to, again, 2 times our mass, same mass, times our new r squared. So let's write that out as 2 times our mass. Our mass is 2 kilograms, 2 times 2, times our new r squared, but our new r squared is going to be 1/10 as much. So we've got to square that. So we're going to end up with 4 divided by 100. And that's going to be times omega. Final. Well, we don't know what omega is, but we're able, because we know how these masses are moved in, we got these masses real close to the person's chest, just 1/10 of a meter away. And if we can neglect the person, we know that this equation has to work. Well, what does this equation say? Well, the 4 is going to cancel with the 4, and our new omega, our final omega, is going to equal to 100 times pi. You're going to spin at 1/100 times your previous angular velocity, which tells us that in a practical situation, we probably couldn't get that much mass that close, and we couldn't ignore the platform and the moment of inertia of the person, which would slow that down. But if they did that, and you started with something like pi, you'd have 100 times as much finally as you had initially. And that tells you, if you've watched ice skaters, how they're able to get those incredible spins that they get in a very short length of time. The same is true of a diver going off of a diving board. If you look at a diver as they go off, and here's the water down here, when they go off and they form and they want to do a flip, they take their body and curl it up, and then right before they come out, hit the water, they straighten their body out at exactly the right time, so that enables them to flip up, get an angular velocity like this, contract and spin very rapidly, so that they can effectively do maybe 2 or maybe even 3 flips or complete turns or revolutions prior to going into the water. And when they straighten back out again, they try to do this so that they're exactly angled to go into the water. So that's a perfect example of the angular momentum. And it's very often the case that we now take every one of the rotational concepts and calculate that for something like a bicycle wheel or something else where we have both a dynamical situation that involves translations and also involves rotations.